In the last video, we talked about the basic ideas of anti-differentiating. And remember the idea when we're anti-differentiating, we're working backwards through the process of taking a derivative. And then we also talked about some rules for anti-differentiation, that basically the antiderivative of a sum was a sum of the antiderivatives, antiderivative of difference of the antiderivatives, the antiderivative of a constant times a function is a constant times the antiderivative of the function, and the antiderivative of x to the r was x to the r plus 1 divided by r plus 1, plus, of course, that constant of integration. So let's use these now to take some antiderivatives of more complicated functions. And so let's look at this situation here. We have the antiderivative of the quantity 3x to the fourth plus 2 cosine of x minus 4 times the square root of x plus 5 over x. And so to take this antiderivative, now I'm going to write out more steps than you probably would do in your homework or such or on an exam, but just to make sure that we're clear on this, remember we can break up sums and differences and do the terms separately. So we can take the antiderivative of 3x to the fourth dx plus antiderivative of 2 cosine of x dx minus antiderivative of 4, I'm going to call this x to the 1/2, all right, plus of dx plus antiderivative of 5 over x dx. Then we can take these constant factors out, so this would be 3 times antiderivative of x to the fourth dx plus 2 times antiderivative of cosine of x dx minus 4 times the antiderivative of x to the 1/2 dx plus 5 times the antiderivative of 1 over x dx. And now remember the power rule. Let me just write it down below here in blue. The antiderivative of x to the r with respect to x was x to the r plus 1 over r plus 1 plus a constant. So this is going to be 3 times r here is 4, so x to the 4 plus 1 over 4 plus 1 plus a constant. I'll call this constant c1. Okay, because it comes from the first term. Then plus 2 times, now we're asking what function has cosine as its derivative? Well, of course, sine has cosine as its derivative, so this would be sine of x plus a constant of integration c2, all right, minus 4 times, now again I'll use the power rule, r here is 1/2, so I'd have x to the 1/2 plus 1 over 1/2 plus 1 plus another constant c3, and then plus who has 5 times who has 1 over x as its derivative? Well, that would be the natural log of x plus c4. And so notice that this is going to be 3/5 x to the 5th plus 2 sine of x. All right, and then I have minus 1/2 plus 1 is 3/2, so I have 3/2 on the bottom here. That would be like 2/3 on the top. 2/3 times -4 is -8/3 x to the 3/2. All right, and plus 5 times the natural log of x plus, and now I have c1 plus c2 plus c3 plus c4. Now notice c1 is a constant, I don't know what it is. c2 is another constant, don't know what it is. c3, same thing, constant, don't know what it is, and so on with c4. So all of these, I mean, these numbers could be anything. And so altogether they could be anything. So usually what we do is, instead of going term by term and introducing that constant of integration, we save them all and combine them and have just one composite constant of integration that I'll call C at the end. So this would be 3/5 x to the 5th plus 2 sine of x minus 8/3 x to the 3/2, right, plus 5 natural log of x plus c. And so that would be antiderivative of this. I should say one more thing. If you recall, the derivative with respect to x of the natural log of x is 1 over x for x greater than 0. Okay? The derivative with respect to x of the natural log of the absolute value of x was 1 over x for x not 0. And so an antiderivative of 1 over x could be the natural log of x, of the absolute value of x, if you don't know what is happening to what's the sign on x's. So I probably should be calling this the natural log of the absolute value of x. Okay, because I don't know whether x is positive or negative. It can't be 0. If it were 0, we have trouble with our original function. All right, let's take a look at another example. All right, let's calculate antiderivative of 3 over q to the 4th plus 5 plus sine of q over cosine squared of q dq. Okay, well, again, we could divide this up, and I'm going to do this a little bit quicker here. I'm going to write this as the integral, as 3 times, I'll take the factor 3 out, the integral of q to the negative 4th dq, all right, plus 5, well, I'll write this way, integral of 5 dq, all right, plus the integral of sine of q over cosine of q. That's going to be the integral of sine of q over cosine of q times 1 over cosine of q dq. Now this, using the power rule, all right, adding 1 to the 4, this is going to be 3 times q to the negative 4 plus 1 over negative 4 plus 1. All right, then we have to ask, who has 5 as its derivative when we take the derivative with respect to q? Well, 5q, if I take the derivative of 5q with respect to q, I get 5. So it'd be 5q. All right, and then this last one, I want to write it one more time. Notice this is tangent of q times 1 over cosine secant of q dq. And so let's see, now we have to ask ourselves, this is going to be a 3 over negative 3 negative q to the negative 3rd plus 5q, right, plus, and let's see, who has tangent times secant or secant times tangent as its derivative? Well, that is, of course, secant of q. And then remember, we have to add, when we get done taking all our integrals, we have to add that constant, that combined constant of integration. One more thing we might do to clean this up is we might rewrite this as negative 1 over q to the 3rd plus 5 times q plus secant of q plus c. Okay, I think I have one more example here. I guess I have a couple more examples. Let's take a look at this example. All right, the antiderivative of the 3rd root of x, all right, plus x squared plus 4x to the 7th over x to the 5th. Well, let's rewrite this, and notice that we have a monomial. If you forgot what that means, it means it has one term. expression in the denominator. So we can, there's something that we can do here with this. So let's rewrite this, and I can think of this as the integral of, well, the cube root of x is x to the 1/3 power dx. And now this expression, I can write it as integral of x squared, I'll put these together, over x to the 5th plus 4 x to the 7th over x to the 5th dx. And this will be the integral of x to the 1/3 power dx, plus the integral of, this would be x to the -3rd, all right, dx, plus 4 times integral of x to the 7th, or to the 2nd dx. This is going to be, well, x to the 1/3 plus 1 over 1/3 plus 1 plus x to the -3 plus 1 over -3 plus 1, right, plus 4 times x to the 2 plus 1 over 2 plus 1 plus a constant of integration. 1/3 plus 1 is 4/3, so this would be x to the 4/3, and then 4/3 in the denominator is 3/4 in the numerator, so 3/4 times x to the 4/3, and then I have plus, this would be x to the -2nd and a -2 in the denominator, 1 over -2, let me put the minus sign out front, -1 over 2x squared, and then this would be plus 4/3 x to the 3rd plus a constant. Take a look at one more example. All right, in this case, all right, notice we don't have, this is a binomial. So we can't do quite the same thing that we did before. We can't split it up. But there is a way that we can look at this, and this is how I would suggest one way to do it. Let's take this antiderivative of y squared over y squared plus 1 dy, and I'm going to add and subtract the same quantity. I'm going to write it like this. This would be y squared plus 1 over y squared plus 1 minus 1 over y squared plus 1. Certainly, if we combine those, we'd be back to where we started with, right? Because a 1 minus 1 would just leave a y squared in the numerator. Okay, so this is going to be the integral of 1 dy, all right, minus the integral of 1 over y squared plus 1 dy. And of course, what do I take the derivative of with respect to y to get 1? Well, of course, that's y. And then we have to ask ourselves, what is it that I take the derivative of to get 1 over y squared plus 1 if I'm taking a derivative with respect to y? And you might have to reach back in your memory a little bit, but if I take the derivative of tan inverse of y with respect to y, I get 1 over y squared plus 1. And then I'd have plus a constant of integration. So that's one way to approach it. Another way to approach this is do polynomial long division. Okay, and then when you do polynomial long division, all right, you can rewrite it, which basically you'll end up with 1 plus this 1 over y squared plus 1. Okay, and I'll let you try that. And this is some examples of taking antiderivatives.